Hello, I'm Alexander McCrae, and I'm going to be presenting MobilityFirst, an integration approach. So the goal of this project is to look at the ways to improve or add mobility to current internet architectures by default. This is so that we can align with modern workloads better and just make everything a lot cleaner. The solution that we're looking for is to be more generic over specific. We already have a bunch of application-specific ways of solving this, and they work pretty well. So there's no need to replace them for those applications, but to align with modern workloads, we're going to try to do it more generally. We're going to require little to no changes to the protocols that currently exist. So that means no changing the IP or TCP packet format, and it needs to stay compatible with things like NAT and other middle boxes. So as an overview of my solution, it's basically a copy of DNS, but instead of using DNS, it uses GNS, which we'll get into what that is in a little bit. And it provides an API for both peers and the underlying kernel to talk to, much like how DNS works now. And then we'll get into how we can use this API and this daemon to change the semantics of TCP, very similar to the end-to-end approach paper from MIT, and allow for peer mobility in TCP. So the solution goals, it needs to handle all forms of mobility. It needs to be compatible with existing internet architectures. So that's things like NAT and other middle boxes. It needs to be compatible with current existing internet protocols. A lot of solutions already handle it where they create their own protocol. But in order to gain widespread adoption, it needs to be compatible with IP, TCP, and UDP if possible. And it should be a general solution rather than an application-specific one, like how TCP and UDP are. So what are the mobility situations? Well, what happens if the peer moves while being connected to? How does it handle that? If a single peer moves network locations and changes IP addresses, well, how do you handle that? And then if both peers are moving at the same time, how do you handle that? So we're going to look into some previous work done that's sort of inspired my solution. The first one is the end-to-end approach to host mobility. This basically uses DNS and rapidly updates the IP address by basically setting the time to live to 0 on DNS records. And it then includes a token in an optional TCP header to identify the connection. So rather than using IP and port, you're now identified a connection based off a token. It also modifies the TCP state machine to handle these tokens. But it does, importantly, stay compatible with TCP, i.e. if the optional header gets stripped either through NAT or some router along the way, it's not a big deal. It will drop back down to normal TCP. This handles all forms of mobility situations, but importantly, it's using a domain name as an ID, and every mobile peer must have a domain name. The updates are going to take a while. With mobile IP, this is the most widespread adoption of mobility in our current internet architecture. It effectively creates a proxy back to the original peer. So if your peer moves network locations, you're going to route all your traffic back to your home router, and it's going to route it to the peer you're connecting to. This makes it so that the other peer is completely unaware that that you have moved, and it's compatible with existing technologies. It handles all forms of peer mobility. So basically, if both peers move at the same time, as long as they're both using mobile IP, they're both routing back to their home routers, which are routing to each other and then back to them. So it ends up handling that simultaneous mobility. But this requires large changes to internet architectures, although it currently is pretty widespread already, and it's getting more and more. And it breaks the end-to-end principle, which has effects that NAT has and isn't always the best. Quick uses logical connections for mobility. Each connection is given a connection ID. whenever a peer migrates, it will actually probe a path back to the other peer to ensure that it can get there. And then once it's completely migrated, it'll do a little bit of an authentication challenge, which we'll see in a little bit. And then on success, on that authentication being successful, the connection is migrated and they can continue connecting. It has a very, very well defined security model. It handles most mobility situations, and it's compatible with existing technologies as it just sits above UDP. Unfortunately, if both peers move at the same time, they're going to be probing back to the other peer, but they're not going to be in the correct location. You need a third party or some other way of doing it to actually get that simultaneous mobility. So this is MobilityFirst, which I'm choosing to extend, and I think is the best way forward to integrate mobility into our current internet architecture. So MobilityFirst started in 2010 as part of the NSF FIA program, basically giving a clean slate, build the internet up from the ground. Alongside it were the named data networking, which we've studied in class, as along with Nebula, Expressive, and ChoiceNet. There was a prototype of the stack, which I'm proposing that we use parts of as part of my solution. So the components of MobilityFirst that are sort of relevant to the solution I'm going with are the separation of name and addressing. So this is introducing a GUID. The reason we need a GUID is because currently we're using IP addresses as identifiers, and that's not what they are. They are network locations. But by treating them as identifiers, we run into a whole bunch of problems, like what happens when a mobile phone gets a new IP address, or you move your laptop into a new network, right? This IP address is not an identifier. So what we do now is we're going to create a GUID similar to like a domain name mapping down to an IP address. This GUID will map down to the IP address instead, and will actually serve as an identifier for all hosts or all peers. Then we also have a global, fast, dynamic updatable name resolution service called GNS. This is basically like DNS, but instead of mapping down domain names to IP addresses, we're going to map down GUIDs to IP addresses. Then lastly, self-certifying public-private key authentication. This is just a way for us to say, hey, you're claiming to be GUID X and you're at IP address A. I want to make sure that you are actually that GUID. So I'll send a challenge to you to ensure that. Okay, so if we visualize these components, the GNS and DNS are sort of separate, but this doesn't have to be the case. In fact, the GNS and DNS could be the same server or group of servers. One reason we might want this is that currently you'd have to query up to a DNS to go get a GUID for a domain name, and then query the GNS to go get an IP address, right? And that's not really efficient. So what we could do is we could query the DNS right away and get both an IP address and a GUID right away. And that GUID would map to the IP address. And that's sort of one of the benefits of putting them together. So one attempt at implementing a socket library similar to BSD sockets for the MobilityFirst project was MSocket. And this sort of is a replacement for TCP. And instead of it being an IP plus a port, a connection or a client ID and a server ID identifies a connection. It uses multiple TCP sockets under the hood, and we're going to call these are flow paths. And it basically means that any packet you're sending between two peers can travel over any or all of these flow paths. It uses a listening socket, which is the connectionless control socket, to handle migrations. So this is how the two peers will talk to each other outside of TCP to handle migration. So if one peer moves, it'll tell the other peer, hey, this is where I'm moving to. I'll start sending you things from there. It's really nice because it doesn't really require any changes to existing internet architectures, including NAT. For NAT, it does a reverse proxy outside of it. And it handles all forms of peer mobility. Unfortunately, it's not compatible with existing protocols, although fallback is possible. So you could potentially fall back to TCP. And it's more of an application-specific solution because not everyone's going to be using this. Because it's not compatible with normal TCP. It's more meant for single companies or single applications. I have a talk on this. I did my paper review on MSocket in particular. So if you want to know a little bit more in depth on how it works, I highly suggest you go check out that talk. So now we're going to get into my solution. So as a quick overview, there's MobilityD, which is a daemon that handles the GNS interaction and verification of GUIDs. And then the TCP modification using MobilityD is basically an example of how we could use MobilityD to implement mobility in TCP, but it also could be used for a quick protocol or a UDP-like protocol. So MobilityD is a user space daemon. It handles all the cryptographic verifications and challenges, and it handles the logic of mapping GUID to IP addresses. It also handles the interaction with the GNS. So this is basically similar to how BSD's by9 would work with DNS and the kernel. Yeah, so it's very similar to DNS. It allows for upcalling through the kernel, and it allows for many other ways to interact with the service. This is similar to connectionless control sockets from the MSocket. Here we can see the API. So basically we have, we can get the IP address for ourselves, or a remote peer could query our GUID, sorry. And then we can map GUIDs down to IP addresses. The reason this is optional is because a GUID may not have an IP address at the time. And so then we just return none. So it's either some IP address or none. Get GUID from IP is basically a local mapping of IP addresses back up to GUIDs. And then verify self challenge is basically taking in one of those cryptographic challenges and verifying that we are the GUID that we say we are. Challenging an external IP address is basically doing the same against another peer. So we're ensuring a peer is who they say they are. So now we'll get into the TCP modification. And this version of it is actually going to use an optional header, very similar to how the end-to-end approach to host mobility used a token in an optional header. And this time we're just going to send GUIDs in that optional header. So this time connection is identified by GUID port, instead of IP port. Whenever a new packet is received from a new IP address, we have to check to make sure that it has a GUID. And if it does, then we have to see, we have to send a challenge to ensure that that packet is actually coming from that GUID. And then we can just use it like normal. When a timeout occurs, we have to requery the GNS to retrieve the updated IP address if there is one. The TCP state machine stays completely the same, except for the new incoming packets from a new IP address. We still have to check if those are coming from a GUID that we know. So what happens at connection time if a peer moves? Well, a timeout will occur, right? Because we're going to be sending packets to an IP address that isn't listening. And then we're going to requery the GNS, get this new IP address, and then go off. And we can start sending packets again. If a single peer moves IP addresses, we retrieve a packet from this new IP address. And if it has the GUID optional header, we challenge the peer to ensure that they're that actual GUID. And then we continue transferring like normal. If both peers at the same time move, there's a timeout that occurs because both peers will be sending data to the wrong IP addresses. They'll both requery the GNS via MobilityD. They're going to challenge each other to ensure that they are who they say they are. And then they're going to continue transferring. Doing the challenge first ensures that we don't leak any data. Okay, so what about compatibility with TCP? It's really important that we stay compatible with TCP if we ever want to see this get any adoption. And basically, if a GNS header isn't sent, we just fall back to normal TCP. So if a peer migrates and it's no longer able to send a GNS header, well, we can no longer verify that it is that GUID, and therefore we cannot, we can't continue that connection. But if on connection, a peer cannot send a GNS header, the optional GNS header, then we just go back to normal TCP. In conclusion, this handles all the forms of mobility pretty well. It's compatible with TCP implementations, which is really important. And then it's compatible with existing internet architectures. I've ran out of time, so I'm not able to go into how it handles NAT, but the paper does cover how NAT is handled. I just wanted to say thank you to the teaching team. The term has been fantastic, and I love learning about computer networking. Thank you.